So I want to take you back to a very specific and very visceral moment in time.
Oh, boy.
Yeah. You're 16 years old. You're sitting in a drafty school hall on one of those hard plastic chairs that just hurts your back after about 5 minutes.
Right. The ones that always wobble a little bit.
Exactly, the wobbling chairs. And the clock on the wall is ticking way too loudly. Tick, tick, tick. And you've got a math exam sitting right in front of you.
I can literally feel my heart rate going up just hearing that description. It's such a universal core memory, isn't it?
It really is. And you turn the page feeling okay, and then boom, question number 24. It's worth 5 marks, which is huge.
Massive.
And it's this sprawling, messy geometry problem. There are triangles inside triangles, squares wedged into corners, random intersecting lines going everywhere, and it just looks absolutely impossible. Do you remember that cold sweat?
Vividly.
Yeah.
That's the classic brain freeze moment. It's that fight or flight response kicking in.
Yeah.
But you can't fight the paper, and you obviously can't run out of the hall.
Right, you're trapped.
Exactly. So you just end up staring at the diagram, kind of praying the answer will magically float off the page.
And usually what happens, you spend 10 minutes staring, maybe you scribble some nonsense just to look busy, and then you move on in total defeat, leaving those 5 marks on the table.
Yep.
But today we are doing a deep dive into something that claims to fix that exact moment. We've been looking at a really fascinating breakdown by a math educator named Chetan Jayasingani, and he makes a pretty bold promise.
It is a massive promise. He claims that you can actually solve these complex, impossible 5-mark geometry problems in literally under 2 minutes.
Now, I have to be honest here. When I first saw solve geometry in 2 minutes, my skeptical radar went all the way off.
Sure, naturally.
I thought, okay, is this just a gimmick? Is this some clickbait trick where you just memorize a pattern and hope for the best?
Right, like a life hack.
Yeah, exactly.
Yeah.
But as we unpacked his material, I realized this isn't a magic trick at all. And it's definitely not cheating.
No, not even slightly. In fact, I'd argue it's the total opposite of a trick. It's a masterclass in critical thinking.
Yeah.
Because what Jayasingani is teaching isn't really about math, or at least not just about math.
Right.
It's about completely rewiring how you process information under extreme pressure. It's about shifting your focus from the panic of the problem to the actual resources you hold in your hand.
And that is exactly what hooked me. So our mission today for this deep dive is to unpack this method. We're going to walk through a specific nightmare problem that he uses as a case study. We're going to break down his given data philosophy.
Which is brilliant.
It really is.
Yeah.
And honestly, even if you haven't touched a protractor since like 2005, stick around. Because the logic we're discussing today applies to way more than just triangles.
Okay.
Absolutely. It applies to any situation in life where you feel overwhelmed by a goal that you just don't know how to reach.
Yeah, this is essentially high-stakes strategy disguised as algebra.
So let's get into the philosophy first. Before we even look at a shape on a page, Jayasingani sets out a golden rule for geometry. And I have to say, for a math teacher, it's a pretty aggressive rule.
It is, isn't it? He basically says that the given data, the information the question actually freely gives you, is the most important thing in the universe.
Mm-hmm.
And the to prove part, the actual question asking you to find X or Y, he literally says, let it go to hell.
Let the question go to hell. I just love that. It feels so rebellious. It's like the punk rock approach to standardized testing.
It really is.
But practically speaking, is that actually good advice? Just ignoring the question.
Well, it sounds entirely counterintuitive.
Okay.
But think about why we panic in that exam hall in the first place.
Because we don't know the answer.
Right. We panic because we look at the final answer, and it looks like it's a million miles away. We have absolutely no idea how to cross that gap.
Yeah, the gap is terrifying.
Exactly. So Jayasingani is arguing that the to prove part is actually a dangerous distraction at the start. It just consumes your mental bandwidth with worry.
So if we aren't looking at the question, what are we actually supposed to be doing?
We look at the ingredients. The core logic here is that the solution must inevitably come from what is given. The exam board, or in real life, the situation you're in, didn't give you that data just for decoration.
Right. They're not setting the scene for a novel.
Exactly. Every single piece of information, every line, every angle mentioned is a tool. If it's there, it has a specific utility. It's a key.
It reminds me of those cooking competition shows.
Oh, yeah.
You know, like Chopped. If I hand you a basket with eggs, flour, sugar, and cocoa powder, and I say make a dessert,
Yeah.
you don't stand there panicking about how to make a lasagna.
No, definitely not.
You look at the basket and say, okay, I clearly have the stuff for a chocolate cake.
That is the perfect analogy.
Yeah.
You have to extract the information first. Before you even care what the goal is, you list every single property of the objects you've been handed.
Yeah.
You drain the given data of all its secrets.
Drain it dry.
Yes. And only when you've done that do you even allow yourself to glance at what you're supposed to prove.
All right, I really want to put this to the test. So we need to visualize the scenario from the source material. For everyone listening, I'm going to paint a picture.
Let's do it.
It's a classic geometry nightmare. Picture a large triangle. Let's just call it triangle ABC. And let's say angle A, the top point, is a sharp right angle, 90 degrees.
Got it. Big triangle, right angle at the peak, standing up.
Exactly. Now, inside this big triangle, shoved all the way down into the bottom corner, is a quadrilateral, a four-sided shape, labeled DEFG.
Okay.
And the problem simply tells us that DEFG is a square.
Right. So we have a square stuck inside a right angle triangle resting flat on the bottom line. It's kind of like a box sitting on the floor of a triangular attic.
Perfect visualization. Simple setup, maybe. But then comes the to prove part. The question wants us to prove that FG squared equals BG times FC.
And there's the panic.
Yeah, I'll be honest, looking at that equation, FG squared equals BG times FC, my brain just immediately shuts down. It looks like a nasty algebraic mess.
It doesn't look like geometry at all.
Not at all. It looks like random letters multiplied together. My instinct right away is to say, I have no formula for this and just give up.
And that right there is exactly where most students fail. They stare at that equation, the target, and they freeze.
Yeah.
Jazzinani says that is the exact moment you need to tell the equation to go to hell.
Go to hell, FG squared.
Exactly.
Yeah.
Ignore it entirely. If you stare at the target, you'll never move. Instead, ask yourself, what do I actually have?
Okay, sticking strictly to the method. I'm ignoring the scary algebra. What do I have? I have a big triangle with a 90-degree angle at the top, and I have a square inside it. That is literally it.
Right. So step one is unpacking the square. The source says we need to drain this square of all its hidden information. If I tell you something is a square, I am actually telling you 3 or 4 different things implicitly.
Yeah.
What are they?
Well, the basics. A square has 4 corners, and they are all 90 degrees.
Correct. So immediately on your middle diagram, you mark all 4 corners of that inner square as 90 degrees.
Okay.
And crucially, because they're sitting on a straight line, the base of the big triangle, the angles right next to them on the outside of the square, are also 90 degrees. That's data point 1. What else?
Well, all 4 sides are equal length. So the top, bottom, left, and right sides of the square are exactly the same size.
Vital information. Write that down mentally. Side DE equals EF equals FG equals GD.
Got it.
But there is one more property of a square that people almost always forget. And the source highlights this as the absolute game changer.
Oh, right. A square is also a parallelogram.
Yes, which means what?
Which means opposite sides are parallel.
Exactly. The top side of the square is perfectly parallel to the bottom side of the big triangle. And this is where Jazzinani says if you have eyes, use them. Because if you have parallel lines inside a triangle, you have just unlocked a massive shortcut.
You're talking about corresponding angles, right? I remember that term from school, but honestly, remind me how it works.
Sure. Imagine a ladder leaning up against a wall. The rungs of the ladder are parallel to the ground right.
Yeah.
The angle the bottom rung makes with the side of the ladder is exactly the same as the angle the top rung makes. They literally just copy-paste the angle upwards along that straight line.
Okay, so in our problem, the rungs are the square's top and bottom sides, and the side of the ladder is the slanted side of the big triangle.
Exactly. So look at the bottom left corner of the big triangle. Let's call it angle B. Because of the parallel lines, that angle slides right up the ladder. It appears again inside the triangle, just above the square.
Oh, I actually see it. The angle at the bottom left of the big triangle matches the angle at the top left of the square.
Precisely. And the exact same thing happens on the right side. The bottom right angle slides up to become the top right angle. This is the observation step.
Wow.
Notice we haven't done any actual math yet. We haven't written a single algebraic equation.
Not one.
We're just marking the diagram with everything we know must be true simply because of the word square. We found 90-degree angles, equal sides, and matching corresponding angles.
Okay, so our basket of ingredients is totally full now. We've extracted everything we possibly can from the word square. Now, and only now, does the source say we are allowed to look at the scary question.
Now we are ready. Step 2 is decoding the proof. So bring that scary equation back. FG squared equals BG times FC.
It still looks pretty scary to me. I still don't see how ladder angles help me with FG squared.
It does look abstract, but let's play with it a bit. FG squared is really just FG times FG.
Right.
So we have FG times FD equals BD times FC. Now here is a brilliant pro tip from the source. In the world of triangles, we don't usually multiply sides together like this. It's awkward and doesn't tell us much, but we do work with ratios all the time.
Ratios. So you mean fractions?
Exactly, fractions. If I rearrange that equation using very basic algebra, I can turn the multiplication into division. I can bring one of the FG's to the other side and bring the BG over.
So cross-dividing.
Yes. It becomes something like BG divided by FG equals FG divided by FC.
Okay, I'm with you. BG over FG equals FG over FC.
And this is the major aha moment the source builds towards. In geometry, when you see a ratio of size, when you see this side divided by that side equals this side divided by that side, what are we actually dealing with?
Oh, that's similar triangles?
Bingo. We aren't solving an algebra problem at all. We are solving a similar triangles problem. The weird multiplication equation was literally just a disguise. It was a mask.
That makes it feel so much more manageable. It's like unmasking the villain at the end of a Scooby-Doo episode.
Yeah.
It wasn't a ghost, it was just old man similarity all along.
It almost always is old man similarity. So now we just have to locate the actual players. We have this ratio involving the lines BG, FC, and FG. Look at the diagram. Where is BG?
Let me think. BG is the bottom left corner. It's the base of that little triangle on the left that's kind of sticking out the side of the square. Let's call that the left triangle.
Good. And where is FC?
FC is on the totally opposite side, the bottom right corner. It's the base of the little triangle on the right triangle.
So to get this ratio to work, logic dictates we need to prove that the left triangle is mathematically similar to the right triangle.
Okay, but here's where I see a major problem. And the host on the source material points this out too. To prove triangles are similar, you usually need their angles to match right, like AA similarity.
Correct. You need at least two angles to be exactly the same.
Well, looking at the left triangle and the right triangle, we know they both have a 90-degree angle because they're sitting next to the square's corners.
Right.
But that's it. We don't know anything else about them. They are separated by the entire width of the square. They don't even touch. They're like two people living on opposite sides of a massive brick wall. How do we possibly link them?
And this is where we hit step 3, which is the bridge strategy. This is honestly the cleverest part of the source's whole explanation.
I'm ready.
When you can't compare two things directly because they are too far apart or too disconnected, you need a mutual friend. You need a bridge.
A bridge.
Look at the diagram again. Is there another triangle involved here that we haven't talked about yet?
Well, there's the big main triangle, obviously. But, oh, wait, there's the one sitting on top of the square.
No.
The little triangle resting like a hat on top of the box. Let's call it the hat triangle.
The hat triangle is our bridge. We need to see if we can connect the left triangle to the hat triangle first.
Okay, let's check the ingredients we gathered earlier. Comparing the hat triangle and the left triangle. Let's see. They both have a 90-degree angle. Check.
Check.
And, wait, the parallel lines?
Yes. Remember those corresponding angles we marked? The ladder rungs.
The angle at the bottom left, which is inside our left triangle, is the exact same as the angle inside the hat triangle.
Which means?
They have two matching angles. The hat triangle is similar to the left triangle.
Exactly. Now just turn your head to the other side of the shape. Compare the hat triangle to the right triangle.
Okay, hat and right. They both have a 90-degree angle. And because of the parallel lines on the right side, the bottom right angle corresponds directly to the top right angle, so they match too.
So they match.
The hat triangle is similar to the right triangle.
So follow the logic chain here. If the hat triangle is similar to the left triangle,
right,
and the hat triangle is also similar to the right triangle,
then the left triangle must be similar to the right triangle. It's the transitive property. If A equals B and B equals C, then A has to equal C.
Exactly. We have successfully bridged the gap. We have proven that the two little bottom triangles are mathematically similar to each other.
That is so satisfying.
Isn't it? We don't have to force anything. We just use the given data, the parallel lines, to build a bridge straight through the top triangle.
It feels like snapping puzzle pieces perfectly together. Okay, so we've proven the similarity. Now we just need to bring it home to that scary equation from the beginning.
Right on to step 4, the execution. Since the left and right triangles are similar, we know their sides must be proportional. We can write out the actual ratios now.
Right, so we match up the corresponding sides. The standing up side of the left triangle divided by the lying down side equals the standing up side of the right divided by the lying down side?
Yes, let's keep it simple. Short side over long side equals short side over long side.
Okay, let me visualize the letters. BG is the base of the left. GD is the height of the left.
Good.
Then EF is the height of the right. And FC is the base of the right. So the ratio is VG divided by GD equals EF divided by FC.
Perfect. BG over GD equals EF over FC. Now cross-multiply those to get rid of the fractions entirely. What do you get?
Okay, cross-multiplying. BG times FC equals GD times EF. BG times FC equals GD times EF.
Yes.
Okay, looking at the original target equation, the left side is perfect. We needed BG times FC. That's exactly what the question asked for.
Yep.
But the right side is GD times EF. And the question wants FG squared. We are so close, but the letters are wrong. Did we take a wrong turn?
We didn't take a wrong turn at all. Look at your given ingredients one last time. What actually is line GD? And what is line EF?
They are the sides of the square. Say it. The very first thing we said when unpacking the shape, in a square, all sides are strictly equal.
Exactly.
So line GD is the exact same length as line FG, and line EF is also the exact same length as line FG.
You can literally just swap them out. Basic substitution.
So instead of writing GD times EF, I just write FG times FG,
Which is
FG squared. And boom, BG times FC equals FG squared. The problem is completely solved. QED.
And there it is. You went from a terrifying algebraic mess to a fully solved geometric proof.
Yeah.
Just by unpacking the definition of a square and using a third triangle as a logical bridge.
You know, when we walk through it step by step, like this, it feels so completely logical. But Joel Singhani says this is a 2-minute solution.
Right.
Does it realistically take under 2 minutes? Because we've been talking for quite a while just unpacking the logic of it.
It absolutely takes 2 minutes if you trust the process.
Oh.
The explanation we just did took time because we were talking about the why and carefully building the visualization.
True.
But imagine you're sitting in the exam room and you already know this method by heart. Step 1, you see the word square. You instantly mark your 90 degrees and your parallel lines. That takes maybe 15 seconds.
Okay.
Step 2, you see parallel. You immediately mark the corresponding angles. Another 15 seconds. Step 3, you see the ratio target. You realize, oh, I need to match the left and right triangles.
Right.
Step 4, you see they don't touch, so you look up. Hat triangles, obviously the bridge. Step 5, you quickly write down the similarity steps and substitute the square sides. You are done in well under 2 minutes.
It's basically the difference between wandering around a pitch black room desperately looking for a light switch versus having a glowing map of exactly where the switch is.
That's a fantastic analogy. The given data philosophy actively creates the map for you. Most students spend their first 5 minutes just feeling around in the dark, staring at the trumpery and panicking.
Yeah.
Jazingani is just saying, turn on the lights first. Look at what is actually in the room with you.
What I really deeply appreciate about this source is that the teacher in the video isn't just teaching this one specific math sum. He explicitly says, I don't want you to learn this sum. I want you to learn the approach.
That is the mark of a truly great educator. He knows you probably won't ever get this exact question with these exact letters on a real test.
Right. The odds are 0.
But you will absolutely get a question where you have resources, the given data, and a goal to prove. And the core lesson remains the same. The path to the goal is always hidden inside the resources.
Always.
It's not a magic leap of faith. It's a systematic extraction process.
It's funny because if we zoom out a bit from the math, this is actually a really powerful life lesson. I know that sounds maybe a bit cheesy coming from a geometry deep dive, but hear me out on this.
No, I'm totally with you. Connected.
Think about how often we face a massive problem in our real lives, like I need to buy a house or I need to completely switch careers.
Big goals.
Huge goals. And we just stare directly at the proof. We stare at the massive, scary end goal, and we paralyze ourselves completely because we just don't see the immediate path from A to Z.
And in doing that, we completely forget to look at the given. We forget to stop and ask, okay, what do I actually have right now today? What are my existing skills? Who is in my network? What specific resources are already sitting in my basket?
Right. We try to solve the terrifying algebra before we've even unpacked the square sitting right in front of us. We try to jump straight to the finish line without realizing we have parallel lines that can easily act as a bridge.
That's the essence of critical thinking right there. Panic is focusing entirely on what you lack, which is the answer. Strategy is focusing entirely on what you have, which is the data.
I love that. Panic focuses on what you lack. Strategy focuses on what you have.
Jazinggani's method is essentially a brilliantly simple anti-panic algorithm. Ignore the scary thing. Look closely at the familiar thing. Work forward logically from there.
Let the scary thing go to hell. I think I'm genuinely going to adopt that as my personal mantra for the rest of the week.
It's a highly effective mantra, whether it's geometry or, I don't know, project management at work. If you meticulously map out what is true right now, the very next step usually just reveals itself to you.
It really does. You don't need to miraculously know how to prove those two bottom triangles were similar initially.
Not at all.
You just needed to faithfully mark the angles that the parallel lines gave you, and the similarity just naturally emerged on the page.
It emerged directly from the data. That's the beauty of it.
It's genuinely cool. So let's wrap this up with a quick recap for everyone listening who might be driving or at the gym and couldn't take notes. What are the 3 big takeaways from this deep dive?
First rule, don't ever look at the question first. Look solely at the data. Let the goal go to hell until you fully understand what materials you're working with.
Love it. Second,
unpack every single definition. If a problem says square list, absolutely everything a square is. Angles, sides, parallel lines. Drain that word totally dry of clues.
drain it dry. And the third takeaway.
Third, use the bridge technique. If 2 things you need to connect don't touch or seem unrelated, look for a third mutual thing that they both connect to.
Perfect. And I'll add a bonus one. Don't forget the Scooby-Doo reveal. If you see a weird multiplication equation in a geometry problem, it is almost always just similar triangles wearing a mask.
Absolutely. And once you learn to see that, you really can't unsee it.
You really can't. This deep dive has actually made me want to go find and solve some math problems, which is honestly a feeling I haven't experienced in about 15 years.
It's the joy of the puzzle. Because once you finally have the right tools, it stops being a stressful test and starts being a really fun game.
It does. We really hope this deep dive gave you a completely new way to look at those impossible problems, whether they happen to be on a high school math paper or just sitting in your email inbox right now.
Indeed. Strategy is universal.
It is. Before we go, though, here is a final thought for you to chew on. We spent a lot of time today talking about how the solution was sitting right there in the given data the whole time, just waiting to be unpacked.
Right under our noses.
Exactly. It really makes me wonder, how many completely unsolvable problems in your life right now actually have the solution hiding in plain sight, just waiting for you to stop staring at the obstacle and start taking a serious inventory of the resources you already have?
That is the real question to ask yourself today.
It is. Thanks so much for listening to The Deep Dive. We'll see you next time.